We present a simple, efficient method that takes an input video and both computes temporally consistent optical flow vectors and approximates stable video solutions for various applications. For example, here we show a spatial temporal scribble propagation. Our method works by separating the data and regularization terms of many common image-based optimization problems. We then replace the costly global regularization step with the novel, temporally consistent, edge-aware filter. The efficiency gained from this approximation allows us to solve optimization problems over entire video volumes, yielding stable results and allowing us to introduce long-reaching temporal constraints that help resolve ambiguities. A naive implementation of an edge-aware temporal filter would be convolution with the content-dependent kernel centered around an ellipsoid in the video volume. However, this does not account for the important issue of object motion between frames. We implement a separable edge-aware filter that correctly models motion paths when filtering in the temporal direction. Here we show an example of a temporal kernel through a video volume. Our method both uses and computes optical flow. This chicken and egg problem is solved by iteratively updating our current flow estimate. We first initialize our space with sparse feature correspondences, which are then filtered in alternating x-y temporal passes. Using this simple approximation to the global solution, we show that it is possible to achieve good quality results over a number of applications. We first compare our optical flow to a state-of-the-art single-frame optical flow method using standard Middlebury coloring to represent flow vectors. We can see that by enforcing temporal continuity, we can not only resolve ambiguities, but we can also produce outputs that are stable over time. This example shows a comparison to a high-quality, fast temporal sliding window optical flow approach. When the whole scene changes color, this corresponds to shaking of the handheld camera. Here we compare our method to a state-of-the-art temporal variational optical flow approach. We use an alternate method to visualize our flow vectors by interpolating between two input frames on a difficult example that exhibits multiple object motion directions and significant motion blur. In the right, the motion border between the scooter and the car is incorrect, creating a tearing artifact. In this case, on the right, we can see that the entire street moves more with the motion of the car. Even though there are few distinguishing features on the road to determine its motion, our efficiency allows us to use greater amounts of temporal information to resolve the ambiguity. We now look at the application of depth upsampling. Using input depth and video from a Microsoft Kinect camera, our method performs a temporally consistent joint upsampling. Holes, shown in gray on the right, are filled using information from both spatial and temporal neighbors. We can also see that temporal noise has been reduced. For computing visual saliency, our method uses a per-frame saliency computation for initialization and then filters it temporally along motion vectors. We validate the quality of our results in a retargeting application, where the video aspect ratio is changed without stretching the important object. Wobbling can be seen when using the original saliency. However, these artifacts are largely reduced in our method. We apply our method to scribble propagation and colorization, showing the input scribbles on the right. This is a comparison of our approach to a global colorization solution. The top row shows the original scribbles, and the bottom row shows the colorized output. We can see that our approximation can occasionally cause bleeding artifacts at object boundaries. These artifacts can be easily reduced by simply adding a few more strokes, as shown here. Our method can be used for disparity estimation as well. Here we compare our result to a state-of-the-art semi-automatic disparity estimation technique. Here we compare our results to state-of-the-art disparity maps provided by the MPEG group. To better illustrate the differences, We will now show some objects virtually inserted into the scene at specific depth levels. This is a result using the MPEG disparity map. And this is the result using our disparity map. Notice that the edges more faithfully correspond to object boundaries and that the map as a whole exhibits less temporal noise. Thank you for your time.